Hello, ladies and gentlemen, and welcome back. We're still looking at the open paper from 2015, and this time we're up to question B3. So if you haven't taken a look at it, I would encourage you to do so. Here's the question, give it a try, and we can proceed. So what have we got here? An arithmetic sequence is a sequence where each term after the first is the sum of the previous term plus a constant value. So this is sometimes called the common difference, often denoted D. For example, 3, 7, 11, 15, and so on is an arithmetic sequence. We start with 3, and then to get the next term we add 4. And then to get the term after that, 4, add 4, add 4, and so on. Alright, so we've got capital S. It's a sequence with the following properties. The first term of S is positive. Okay. The first three terms of S form an arithmetic sequence, which is why they tell us what an arithmetic sequence is. Now, they say the first three terms. Are there more than three terms, and it just isn't an arithmetic sequence after that? Seems to be the suggestion. If a square is constructed with area equal to a term in S, then the perimeter of that square is the next term in S. We want to determine all possible values for the third term of S. Okay. So usually when they ask for a specific value, it's a good idea to give that a variable name, maybe t for third term. Now, this third condition here, I'm quite interested in it because it seems to be how we make the sequence. Okay, we always start with a positive term, so if that were equal to the area of a square, which wouldn't be that bad, then we'd get the perimeter of that square as the next term. So a good question would be, if you've got a square with a particular area, how does that, so A is the term in our sequence. What's the next term? Well, if we call the side length S, A is equal to S squared. And the perimeter, well, how do you find perimeter for a square? All the side lengths are the same, so it's just 4 times the side length. So our next term should be 4S, and that's the perimeter. So we go from S squared to 4S. Okay. So I guess one way to go forward in our equation is if you've got a term x, the next term should be the square root of x times 4. Or if we know a later term, which I think we should probably focus on because we want to talk about the third term, if we know a later term, x, how do we get the previous term? We divide by 4 and square. So what's our focus? Well, we know that the first three terms form an arithmetic sequence, and we've given a name to the third term. Why? Because that's the thing we want to solve. So I guess we could work backwards. The second term looks like this. And the first term, once again, divide by 4 and square that. So we could clarify this a little bit. T over 4 squared would be t squared over 16. T squared over 16. Then we want to divide that by 4, so that'd be t squared over 64. And that'd be t to the 4 over 64 squared. So that would be, oh gosh, what would that be? 64 times 64. Is it 4096? I feel like it is. 4, carry the 2. Yeah, 4096. So, big numbers, but not ridiculous numbers, especially if you're in computer science, because it's just powers of 2. Okay, so I understand what my first three terms must look like. And with this t to the 4 here, in order for the first term to be positive, well, fourth powers are always positive or 0. We just need t to not be 0. So we'll make a little note about that right away. So if we ever reach a situation where t is equal to 0, we can know that we can ignore that case. Okay, so those are the first three terms, but what do we also know? That there's this common difference. So I might say let D be the common difference because the first three terms form an arithmetic sequence. So t squared over 16 is equal, so the second term is equal to the first term plus this common difference, and t is the second term plus this common difference, which could also be written as the first term plus 2 copies of this common difference, whatever the common difference is. Okay. So we've got 2 equations here and 2 unknowns, the d's and the t's. We should be able to solve this. I guess it might just be really easy to rearrange this expression here and say d is t minus t squared over 16, and then I guess we could plug that in here and just really quickly get rid of the d value. So we get t squared over 16 is equal to t to the 4 over 4096 plus t minus t squared over 16. And we can rearrange this. We're not quite going to get a quadratic, but well, let's actually bring everything over to the one side. So 0 is t to the 4 over 4096 minus 2 copies of t squared over 16, which is really t squared over 8, plus t. Now I can factor out a t here. So if whatever our third term is, it's going to satisfy this expression. I can also multiply by 4096. I'm not sure if I want to do that, but definitely think it might be a little nicer. So 4096 divided by 8, well, 4096 is 8 squared times 8 squared, so we're just looking for 8 cubed, which is 512. Let me get this t here. Okay. So I can definitely take out a factor of t cubed, or not t cubed, t, and then I'm left with this t cubed. I'm left with a cubic, and I don't like having to try and solve cubics. It makes me uncomfortable, because I don't have the cubic formula memorized. So, but this would mean that t equals 0, but we already said that that doesn't work. Okay, you can't have t equals 0, otherwise your first term is going to be 0 and it wouldn't be positive. Now, we could, I guess, so t equals 0 doesn't count, since I need t to the 4 over 4096 to be greater than 0. That tells me that t satisfies this expression, t cubed minus 512t plus 4096. Now, this is a this isn't a quadratic. This is a cubic that is at least sort of in a nice form, and I think we could maybe rearrange it a little bit. But, I'm not actually sure what the best way to go about trying to solve this is. Is there any solution that I can see off the top of my head? These are powers of 2, and I'm wondering if I can just maybe factor it in my head, although the fact that it's taking me a while makes me think maybe I can't. But what do we got? We've got 2 to the 9 here, and this is 8 to the power of 4, so that's 2 to the 12. And so I feel like t should be 2 to the something. Maybe? I need the negative here and the positive here to cancel out. And t cubed is probably going to be positive as well. So I need t to be more than 8. Because then this part is greater in negativeness than the 4096 is for being positive, and then hopefully t cubed could make up the difference. Well, I might have to employ another technique to solve this, but let's try a power of 2 that's bigger than 8, so maybe t is 16? Well, then what would we have? We'd have t to the 2 to the 4 cubed minus 2 to the 9, 2 to the 4 plus, oh, this is going to work, 2 to the 12. So this is 2 copies of 2 to the 12, one here, and one here, minus 2 to the 13, which is just 2 copies of 2 to the 12. So 16 is a root, and now I can continue on. So now, does that make sense? Because what would we have? We'd have the first term would be t to the 4 over 4096. That would be t to the 2016 divided by, or sorry, 2 to the 16 divided by 2 to the 12, which would be 2 to the 4. So this would also be 16. And if I have a square of area 16, then the side length is 4, and the perimeter is then going to be 4 times 4, which is also 16. So yeah, yes, we do get an arithmetic sequence with 16. Well, that's kind of nifty. Okay, but if 16 is a root, we should be able to factor it out. So we get t cubed, 0t squared minus 512t plus 4096. T squared, so t cubed minus 16t squared. 16t squared, bring down the 512t. So plus 16t. 16 times 16 is 256. So we get negative 256t plus 4096. And so that should be minus 256, and this is a quadratic. Can I factor this quadratic? That is a fantastic question, and one that we shall find out in just a moment. I don't think so, but what would it be? I don't think the power of 2, well, maybe 8 squared, no. Maybe 16. No, I don't think that'll work. Let's do quadratic formula. So we know we have roots if b squared minus 4ac is greater than or equal to 0. So b squared, so in this case 256, minus 4 times 1 times negative 256. So that's 5 times 256, and that is greater than or equal to 0. Okay, so I do have roots. So let's use the quadratic formula. So by the quadratic formula, t is equal to negative b plus or minus square root of b squared minus 4ac, which we just said was 5 times 256, all over 2a. So negative 8 plus or minus 16 root 5 over 2. So negative 8 plus or minus 8 root 5. However, one of these will be negative. Wait, will one of the... No, not necessarily. I was going to say it has to be negative, otherwise the t to the 4, but t to the 4 is automatically positive. We just can't have 0. Although, now that I think about it, every term in the sequence should be positive, right? Because it's each term. So the first term's got to be positive. They tell us that. Then the next term is the perimeter of some square, and the term after that is the perimeter of some square, and the perimeter of some square. Perimeters are sums of lengths, and lengths are never negative. So yeah, we can't use negative 8 minus 8 root 5, but we can use the positive one. So good catch there. Otherwise, we might have run into a problem. So our final answer is t can be 16 or 8 root 5 minus 8. So those should be our only solutions to the... Those should be the only positive solutions to the quadratic that we got. Maybe a little comment. T is positive since it is a perimeter. And there we go. So those two solutions, and that's what they're looking for. And that wraps up B3, so I'll see you in the next video for B4.